Now that we're dealing with the wave-particle duality, we need to have a look at a bit of an oddity about quantum mechanics. That's to do with Heisenberg's uncertainty principle. I'll try and explain this in a way that's understandable. It's a bit of a tricky one without getting into lots of detailed explanations. So basically just looking at the fact that since every particle has also has wave properties, it means that making some measurements about the particle or the wave is somewhat problematic. So measuring both position and velocity, or more generally, we can take velocity multiplied by mass, and we are looking then at momentum. Measuring either of those two quantities becomes challenging, particularly when we're dealing with the quantum scale. So when we're dealing with everyday objects, those measurements are much easier to make, and we'll talk about why that is very briefly, but on the quantum scale it makes it a very difficult proposition. The reason for that is if we sort of think about the fact that if we're looking at a particle, so something that has those very definitive properties of mass and momentum, so a particle has a definite position at a given point in time. So we can identify where a particle is located, and you could sort of state that in terms of Cartesian coordinates. On the flip side though, if we think about a wave function, it doesn't actually describe a single position. So a wave function, as we looked at, describes the probability of the particle being located at any position. So trying to link those two things together, one that is very definite about where an object is located, and one that is talking about the probability of it being located in a range of different positions, means that the stating the position becomes a bit troublesome. So there's the first thing to sort of store in the back of your mind. Describes the probability of finding the particle at all positions. So if we then take that to the next stage, if we think about the position of an object, we can then also talk about the wave function. And if we think about this idea of the position, if we measure the position, that means basically that where the wave function collapses. And by the wave function collapsing, what we really mean there is that the probabilities across the range of positions are no longer valid. Let's go back a step. If we measure the position to a high degree of certainty, so the wave function does collapse, means that the probability of the object being located at a particular point has increased, while the probability of it occurring at other points has dropped to zero. And so as a result, measuring the position as an object means that the wave function is no longer particularly valid. But we also know that the wavelength of a wave, or of the wave function, the wavelength relates to the momentum of the particle. And we know that because we have that relationship of the de Broglie wavelength, where lambda is equal to h on p. So that then means if we know the particle's position, we can't know its momentum. And that's because if the wave function collapses, there's no wavelength, and so we have an indeterminate momentum. So there's the first problem. Similarly, but in the reverse sense, if we do know the wavelength, so if we can measure the wavelength to a high degree of certainty, that means that we do know something about the momentum. And if we know what the momentum is, then it means that we are a little bit uncertain about the position, because we now have a wave function that again is going to be talking about the probability of where the particle would be located. Now, there are much more detailed explanations as to why these ideas come into play. If you want to have a look at them, by all means go and look up some YouTube videos and those sorts of things. But for what we're doing, we're just going to leave it at that sort of stage. Now, in equation form, we have, it's probably not even really an equation, it's more an inequality. So we have delta x delta p is then greater than or equal to h on 4 pi. Now, what does that all mean? So if we look at what these quantities relate to, going back to the principle that we're dealing with here, it's the uncertainty principle. Delta p is the uncertainty in the momentum. So if we were to make a measurement of the momentum, it's going to have some uncertainty about it. More specifically though, it's not really about the measurement itself, it's more about the fact that we don't actually know much about the momentum or the position, or we can't determine one of them without having some uncertainty in the other. So there's the equation there. So basically we're looking at the fact that the uncertainty in the momentum, or the product of the uncertainty in the momentum and the uncertainty in the position, will always be greater than or equal to Planck's constant on 4 pi. Why it's Planck's constant on 4 pi, don't worry, it's just a constant that you need to be able to identify. But ultimately what it means then is that if you are particularly certain about the momentum, so if the uncertainty in delta p decreases, then the uncertainty in delta x is going to increase. Likewise, if you are fairly certain about its position, so delta x decreases, then delta p will increase. Another way of thinking about this, just to summarize, is that you can never simultaneously, so you can never at the same time know the exact position and momentum. And if we're talking about momentum, we're ultimately then also talking about velocity of an object. Now, this particular aspect is only really significant when we're dealing with the quantum scale. If we're dealing with objects, of like everyday objects, say a ball or a car or anything along those lines, then the uncertainty in the momentum, the uncertainty in the position, we can calculate them with a fairly high degree of certainty. So ultimately, this is really only we're only really going to consider this in terms of the quantum scale.